Now we are going to see the most interesting part of mathematics, proofs. All math is written in the following format: definition, theorem, proof. But that's not how math is discovered, but that's a whole another story. And now we're going to focus on the proof part of this story. I would say within proof, there are two different components. There is the component of discovering proofs, and then there is one of writing proofs. And the best analogy I can think of here is from music. So like discovering a proof is like coming up with your own piece of music, whereas writing proof is like playing a piece of music. One is a creative thing that you can't really teach, but the other one is more mechanical and something that you can learn from practice. So even though the long-term goal is to be able to discover your own proofs and write real complicated proofs, that's not what we'll focus on. We'll focus on how to write proofs properly and what are the guiding principles for writing proofs. The way you learn how to discover your own proofs is just by practice and experience. This just comes eventually. It's not something you can force yourself to learn. But what even is a proof? Let me start by first describing what a theorem is. A typical theorem, not every theorem is like this, but most theorems are of this form, is of the following form. You have a set of hypotheses. And from this hypothesis, the theorem says that a conclusion follows. Okay, and then a proof of this theorem is something that starts with the hypothesis. And from this, you produce a sequence of logically valid arguments. And you finally try to reach the conclusion. That is how a proof is written. That is not how it's discovered. The discovery of proof, so you're still trying to start at the hypothesis and reach the conclusion, but when you're trying to discover, it just goes all over the place, and your goal is to try to get here. It's like being in a maze and trying to find the exit. So you're just moving randomly in different directions. But then when you write the proof, it's like giving the shortest possible path from the starting point to the end point. Before we come to proofs, the first step is to actually understand the theorems. Now, why is this necessary? It's because we as people, as humans, will write theorems in English, but really mathematics is written in the formal language of logic. And so there is always some discrepancy, or there is some loss of meaning between English and logic. So your first goal is to try to unravel the underlying logical statement. So I'll give you an example. There exists a smallest natural number. Let me make this a little more complicated. There exists a unique smallest natural number. Now, of course, it's very intuitive, and you know the answer. The answer is 0, and so the theorem is true. So the habit that we need to develop is to try to convert theorems which are written like this into formal logic. So let's start with looking at the definitions hidden in the theorem. So here we have two things. We have unique and we have smallest. So let's start with smallest. What does it mean for something to be smallest? So I will expand this as there exists a natural number y. The name of the variable doesn't matter, such that for any other natural number x, I don't need other, for any natural number x, y is greater than or equal to x, such a y is unique. Now we can go further and we can try to expand unique. Oops, I see that I've made a mistake above. This should be y less than equal to x. And then uniqueness means that if there was another smallest natural number, then that natural number must be the same as the original one. So this is how you would expand smallest and unique. Now, when it comes to actually writing proofs, we don't do this at the beginning, but we do it gradually. So maybe the first step would be you expand out what smallest means and try to figure things out there. Then you would try to expand out uniqueness and then try to figure things out there. Like I said, it's a non-linear process. You just have to try many things out. Let me do one more example. This is an overview. You don't have to completely absorb everything in the first go, but keep an open mind and look for patterns. That's what you're aiming to do in this chapter. Here's another example. Sum of two even numbers is even. Before we can start proving it, we have to unravel many things in here. So first thing is, or let me just highlight the things that need to be unraveled. You have the notion of sum, then you have the notion of even here, and then finally you have the notion of even here. So let's start expanding out. If I try to expand out sum, I'll get for every even numbers x and y, x plus y is even. So what I've done is I've expanded the term sum of two into for every even number x and y, and then x plus y. And notice what has happened by doing this. I have discovered that hidden in here is a for every quantifier. This quantifier was not visible in the form that was written above. Similarly, if you look at the previous example, even here we have discovered that there exists quantifier. Even the uniqueness statement can be rewritten as for every z, if z is another natural number that is smallest, then z is equal to y. So this goes in here. And here we discover another quantifier. Okay, so when you expand out statements of theorems, you start discovering variable names and quantifiers hidden within their statements. I still have even here and I still have even here. So how would I expand even out? Even simply means that x is equal to 2 times something else. So I'll write this as for every natural numbers x and y, if x is equal to 2k and y is equal to 2l for some natural number k and l, then x plus y is equal to 2m for some natural number m. What I've done is I've expanded x and y being even as x equals to 2k and y equals to 2k for some natural number k and l. And similarly, I've expanded x plus y being even as x plus y equals to 2m for some natural number m. Again, your goal is not to get this in the first attempt, but keep looking at patterns and observe what's happening. So that's the first step. Whenever you have a statement of a theorem, you're trying to unravel it and trying to find the variables hidden in there and trying to find the quantifiers for those variables. We have seen at least a hint of how to prove statements about quantifiers. So I'm just going to recall those quickly. You might expand your statement theorem and realize that it's a there exists statement. If you're trying to prove a there exists statement, then the simplest way to prove there exists is to actually just come up with an example that works. Similarly, if you're trying to disprove for all, then you do the same thing, except this time you'll come with a counterexample. And the reason these two things are connected to each other is because of De Morgan's laws. So proving there exists is the same as disproving for all. And their proofs reflect this fact. This is not the only way to prove or disprove their existence for all. There is one more way that we will see later. It's called proof by contradiction. But for now, this is good enough. Then the other two cases are you're trying to prove for all, or you're trying to disprove there exists. So if you're trying to prove for all, now you're trying to prove a statement that is true for every variable value in the domain. And the way you start the proof is by saying let x be an arbitrary value in the domain. And similarly, if you're trying to disprove there exists, then you do the same thing. And sorry, in this case, you're trying to argue that px is true. So if px were true for an arbitrary x, then it will be true for everything in the domain. On the other hand, if you're trying to disprove there exists, then you would just argue here that px is false. If you take an arbitrary x and show that px is false for any x, then there is no x for which is true, and hence there exists is false. And finally, let me say that we are going to look at these different proof techniques. We're looking at direct proofs, proofs by contrapositive, proof by contradiction, proof by cases, and the principle of mathematical induction. These are separate chapters of the book. But you shouldn't think of these as being exclusive. It is not the case that a proof is either a direct proof, or it's a proof by contradiction, or it's a proof by mathematical induction. Instead, I like to think of these as like chess moves. You can have a long proof in which one part or one move is a direct proof. And then you have another piece which is a principle of mathematical induction. And maybe there is a global thing going on which is a proof by contradiction. So these are more like components, and a proof is made by combining several component pieces together. It's a very interesting process. Proofs can get very, very complicated. So for example, if you want to Google something called Fermat's last theorem, and that proof took hundreds of years to prove, and the proof is like thousands of pages long. And you can imagine how complicated a 1,000-page proof would be. It's just amazing. Yeah, so we will see the basic principles coming soon.